My senior project, what we call it, was the maglev train or magnetic levitation train. So throughout my presentation, I'm going to give explanations on what exactly electromagnet is, a maglev, and what a maglev train is, the components and schematics of my circuit, the whole construction process, testing, and then at the end we'll compare my maglev train to actual maglev train. So the reason I chose the project for the maglev train was it's all about the futuristic technology aspect of it. I thought it was just really, really cool. You know, frictionless motion, high speeds, goes up to 300 miles per hour, and it's better than the actual trains. It's more fuel. It uses no fossil fuels at all, so clean energy. And I thought, in Florida where we have almost no good public transport, I thought, maglev train would probably do well here. So, what is an electromagnet? Just like the name suggests, it's a magnet that is created by electricity. When a current goes through a wire, it creates a magnetic field around it. And let's say you want to make that magnet more powerful, you'll turn it a number of times in order to create a more powerful magnetic field. And in order to make it even more powerful, you can put a core, like an iron nail or some sort of magnetic material, metal, through the middle of the coil, and that'll make the magnet even more powerful. So, what's a maglev train? It's basically a train that uses levitation propulsion, magnetic levitation propulsion, to move it down a track at very, very high speeds. There are two types of maglev trains. There are electrodynamic maglev suspension trains, and then magnetic suspension. And the difference between the two is electromagnetic uses attractive forces to move the train down the track, and electrodynamic uses repellent forces. So, these are some of the components that I used in my circuit. I had to use the magnet wire, the iron rods for the core of my electromagnet. I have some 3D printed spool pieces that I put on the end of the rods, which you'll see later. I have some resistors in my circuit, relays, and that's actually supposed to be controller, programmable logic controller. And one thing that I had to use a lot was this formula. And this formula allows me to calculate the pole strength of my electromagnet, how strong it actually was. The M stands for pole strength, the N stands for number of turns in the wire, the I stands for the current going through the wire, the A stands for the cross-sectional area, and the L stands for the entire length of the coil. So this is a top-down view of my almost finished circuit, you could say. We're going to look at some components here. So over on the left, we have my DC power supply. I have two of them in parallel at 36 volts. I also have my resistors here. These are also run in parallel. They have about, I think 100 ohms of resistance through them. And then next up we have our relays. Now the relays, the simplest way I can explain it, they're kind of like a door that won't allow the current to flow through unless I tell it to. And I can tell it to however often I wish, and get a certain timing for the circuit for the pulse, that electromagnetic pulse, to go through the coil when I want to push forward my train. And like any door, it needs a key. And the key that allows me to open that door is the programmable logic controller, which is over here. It sends a signal to the relay to basically open up that door how often I wish. And in order to do that, I'd have to write a program for that to happen in the order that I wanted and how fast that I wanted. So this is a very intimidating schematic of my circuit. This actually looks worse on my actual circuit than up here. Up here we have my voltage sources. I have my resistors down here on my coils. Down the middle are my relays, and over here is my PLC, my programmable logic controller. So, started the construction process. I got very, very long iron rods, and I had to cut them into 1-inch pieces, and to achieve like a very minimal length for my coil. Because the longer the coil was, the less powerful it would be. So I tried to get as short as possible. This is my classmate friend Ronnie helping me cut those rods into 1-inch pieces there. So I got my rods, and I decided to, let me see if I can test some stuff out. I got some permanent magnets, and I wrapped the coil around the rod to see how powerful it was going to be, or see if I can move something that was magnetic. Over here, you'll see some tiny pieces over here. Those are also resistors, just less power rated. If I ran a certain amount of current through those would burn up and probably would cause a fire, and that's not what we want. But I was able to move some magnets with that small coil. The only thing is, you can see it's very messy. It's kind of coming off of the ends there. So I needed something on the ends to kind of keep the coil contained. And the solution I came up with was these end pieces, these black pieces on the end here, to put on the ends to keep the coil contained. So I was able to 3D print those end pieces using the technology we have here. And I printed a whole bunch of them, and I super glued the rod and the end pieces, and then I was able to turn the coil. The coil has about 500 turns. Each one has 500 to 600 turns. I did hand turn them. I could have probably used a drill or something like that, but I got worse fun than that. And each one gives out about a pole strength of about 30 to 40 Gauss, which is a measurement to how strong the magnetic field is at the poles. So for comparison, your typical refrigerator magnet is about 50. The Earth's core magnetic field is about 25. So this is a video of me testing one of my coils. I wrapped it in tape to keep it kind of clean. Right here, this is a rare earth magnet, very powerful magnet. And right now it's sitting on the table. And in order to get it to move, I had to connect my coil. I turn the switch down, and you can see it go up to the coil. You can see the autofocus circle up there. So, as I built my circuit, it becomes more and more complicated because I needed to have on my track and my magnets going in pulses. I can't have it on all the time, and they needed to go to have it push and then pull, and push and pull the magnet down the train. I have for my train essentially, so that I'm moving down the track, it has permanent magnets fastened to the bottom of it. And in order to move it down the track, I have to have it attract and then reverse the pull of the electromagnets, and then push it away, attract and pull down the track. And so I started to build a track out of this very, very weak wood. And this is the relay again, and this is my the PLC that I had to add into the circuit. So this is the program that I used in order for the PLC in order to get the timing right. Each one goes off about 0.08 seconds at a time. Every 0.08 seconds, one will go off. And I looped it in a way so that when it ends, it doesn't stop. It just keeps on going whenever until I turn the switch off. So this is a video of preliminary track and preliminary train to see if I can get it moving down over the course of 2 coils, and we'll see what happens. So, in the video, you saw the piece, the plastic piece turning, going back and forth. That was because I was switching the poles of the magnets, and the current magnets were trying to line up with the poles. And you also saw that the track was shaking a lot. It looked like it was about to fall apart, so I had to fix that. So I decided to with some help, to make another track out of aluminum, which is a non-magnetic material, so it wouldn't affect my circuit. And so I got some aluminum. We have a U-shaped piece here, and I got some L pieces along the track, and I put my electromagnets down that. I drilled some holes through the bottom of it, where the wires are, so to make it look a little bit cleaner. There, and this is a picture of kind of what it looks like now. So this is the new train that I bought, that we printed out, sorry. That kind of, it sits better on the track, has little end pieces to keep it level and little vertical pieces to keep it from turning around again. We didn't want that. And those are the permanent magnets that are super glued to the model. So in this video, in the beginning of the video, I'll show you the relay. You see the lights going off every so often. The lights will come on and off. And then you'll see me trying to move the train down the track. So as you can see, it didn't go very far. So one of my favorite quotes from my favorite TV show, Mythbusters, is failure is always an option. Unfortunately, I was able to get my train to move down the track as I would like. It goes in short bursts, but there are definitely ways to fix this, and I know how to fix this. And the primary reason is there's not enough current going through these circuits. The magnetic pulses aren't powerful enough in order to push it far enough down the track. And one of the ways to increase that pulse is to increase the current. Another way to do that is to increase the number of turns in the coil. I stopped at 500 to 600 because I did some calculations that seemed like enough, but I didn't account for resistance that was going through the coil. I didn't account for a number of things. And higher current also, the wires that I use probably aren't rated for that type of current. The current that I need to actually move something, if I tried that, the wires would probably melt and destroy my whole circuit. Another reason, another option that I could have done was using AC over DC. AC automatically goes back and forth. It goes one direction then back the other, as opposed to DC when I have with the relays. So if I use a AC source, I wouldn't have a need for the relays or the PLC. But maybe if I improved it, I can get it moving like one of these trains. So, how does it compare? My train uses attractive and repulsive forces, 4 coils, has an aluminum track, weighs 11 grams, it's 2 permanent magnets, powers about 46.8 watts, top speed less than a mile per hour. The actual maglev train uses an attractive force, weighs 17.6 tons, 4.2 megawatts of power used, and it goes over 300 miles per hour. So I'm close. So I'd like to extend special thanks up to Professor Olegandric. Without him, I probably wouldn't be even in this program. Fantastic professor. I'd like to thank Paul Slater. He helped me with the construction of the track and the 3D printing. I'd like to thank Google, because Google's amazing. And I'd like to thank Palm Beach State College for having this presentation, for allowing students to have this opportunity in front of all you guys.